ionic compounds, and it is a metal and a non-metal together. And as we talked about, whenever you have a metal pretty much involved, it is really the most important thing in terms of naming. And in a type 1 compound, the metal is a guy with a fixed charge. So that is basically your group 1, 2, 3, zinc, cadmium, or silver. And to name these guys, we use the whole name of the metal. And our non-metal drops the last part of the name there and replaces it with the IDE here. Type 2 compounds are also ionic. They also are a metal and a non-metal together. And once again, here it is the metal that's most important. And the metal here is a guy that has a variable positive charge. So those are typically your transition metals. Are just to the right where things like lead and tin on the periodic table are also sort of fall under here. Because they do have a variable type of charge, you need to tell everybody sort of what the charge is on the metal when you name these guys. So once again, here we do the whole name of the metal. We do a Roman numeral. And that Roman numeral is the positive charge on the metal. And once again, we're in a room, but this way, our non-metal comes at the end with the IDE at the end of it. We also talked about polyatomic ions. Polyatomic ions are really covalently bonded compounds. They are a bunch of non-metals together, but they do have an overall charge, so they are still ions. Polyatomic ions would be good. You just have to sort of memorize those names and formulas, but for the most part, most of them end in either 8 or ite, typically in a group of 2 or so. The one with the most oxygens have 8 at the end of it, and the ones with the least number of oxygens have ite. In like a group of 4, they additionally put per in front of the guy that ends in 8, and hypo in front of the guy that ends in ite for the group of 4 that come together. And so you sort of have per, for example, chlorate, chlorate, chlorite, and like hypochlorite in sort of a group of 4. In addition, other things that happen with polyatomic ions, sometimes put a hydrogen H plus in front of it. So for example, hydrogen carbonate, which is also sometimes referred to as bicarbonate. Same thing with sulfate, hydrogen sulfate, also referred to as bisulfate as well. What we found and what we talked about was, for the most part, our polyatomic ions are usually mostly negatively charged, which means they do sort of find themselves in a lot of cases kind of hooked up with a metal. So a lot of times what happens when we're dealing with the polyatomic ions is we sort of fall back to either type 1 or type 2 sort of naming. And what I mean by that is, again, it'll be hooked up with the metal. So the metal is most important. So if the metal needs a Roman numeral, you should include it. If the metal does not need a Roman numeral, you would not include it. And with polyatomic ions, we pretty much just use the whole name of the polyatomic ion. We also put parentheses if we have more than one of the polyatomic ions. So we always want to put parentheses around them in formulas. Ultimately, all these guys are pretty much ionic, and that also means that when we do put the positive guy together with the negative guy, it always equals 0. We talked about, I think at the end there, acids, which basically has to do with oxygen. So if there's no oxygen, then it is hydro something ic acid. So again, HF would be hydrofluoric acid, HBr would be hydrobromic acid. So these are the guys that get the hydro in it, the ones that do not have oxygen in it. If it is an acid that does contain oxygen, then it will probably have one of those polyatomic ions in it. And if it does contain oxygen, Then your polyatomic ion ends in 8. Your acid name will be something ic acid. Again, like HNO3, that would be nitrate, being nitric acid. And if your polyatomic ion ends in ITE, then your acid would be OUS acid. And that will be like something like HNO2 here, which is nitrite, be nitrous acid here, OUS. So those that do have oxygen in it that are acids, we do not use hydro for. Again, hydro is just for ones with no oxygen. Any questions on any of that naming stuff that we talked about? Yeah. Okay, the last little part of naming that we're going to talk about, I think, are type 3 compounds. And type 3 compounds are when we have two nonmetals together, they're covalently bonded. They're sometimes referred to as molecular compounds. These are basically, we have our sharing of electrons. And with type 3, this is finally the appropriate place to use a prefix. So this is where we use prefixes. So mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8, maybe nona for 9, deca for 10. So with type 3 compounds, when we have two nonmetals together, we do use prefixes, and they really are sort of the easiest ones to name and sort of figure out. But they are the ones that sometimes people screw up the most on because they're trying to balance out charges and stuff like that, which they do not need to do. So really, you just need to kind of count up how many of each of these nonmetals you have, use the appropriate prefix. When we sort of name type 3, we basically do the appropriate prefix on the first element, and we use the whole name of the first element. And then we use the prefix for the second element, and we give the second element, kind of like everything else we've been doing, it gets the IDE treatment at the end of it with the appropriate prefix. There are a couple rules that we do with the prefix. The first one is mono is never used on the first name. But you can use it on the second. So that's an important rule. No mono on the first name, but definitely can use it on the second. The other thing that sometimes happens with our prefixes is we sometimes will get a couple of vowels that sort of back up to each other, a vowel from the prefix and the first letter of the element, like commonly an A and an O, or an O and an O. And usually what we do is we do drop off the last letter there of the prefix or the vowel, and we get rid of it. So if we had one oxygen, instead of saying monoxide, we get rid of that O and it becomes monoxide here. So that's a very common one that we do. Two I's are okay, actually, it seems to be, but that A and the O and the O are sort of not so good. Any questions on that there? So as I mentioned, the rules are we go first element whole name, and second one gets the IDE. And again, we use the appropriate prefix as long as it is not mono there on the first one. Here's a little table of our prefixes here. And as I mentioned, a couple of other things here. This would be tetraoxide. We do drop the A off of that when we have the A and the O, and it just becomes tetraoxide there without the A. A couple of compounds, especially some of these molecular ones that are just named by their common name, definitely water, as we talked about before, ammonia, CH4, which is methane. These guys should use their common names as well. Now, hydrogen, I think we talked about, but just to reiterate, hydrogen is a non-metal, but for the most part, because it's really part of like an acid and stuff like that, it is sort of treated like a type 1 compound. So if we do have hydrogen coming first, for example, here, that's not an acid, say this was a gas, this would be hydrogen chloride. And it is thought of almost as ions, H plus and Cl minus, even though they're both really nonmetals. Same thing here. If we had H2S, this would be hydrogen sulfide. Again, even though there's two of them, it won't affect the name. So hydrogen's a little bit different how we sort of name it, even though it technically is a nonmetal, and technically they are sharing electrons here. It is sort of treated almost like an ionic compound and sort of named as like a type 1 compound where we just kind of use hydrogen and whatever comes next. Obviously, we also talked about with type 1 guys and hydrogen, if it comes second in a formula, it is the negative version of it, and it would be hydride. So that's sort of an exception, hydrogen, even though it's really non-metal here. We really don't use prefixes or anything like that with hydrogen that's involved. Any questions on that there? All right, so take a couple minutes and a couple seconds here, name these guys. We'll also do some names to formulas. Let's do dinitrogen, trisulfide. Let's do carbon tetrachloride. Let's do dioxygen. Let's do pentasulfide. Nah, that's not what to do. Since I'm making up names, let's go with pentanitride. Okay, let's take a look here. So we see iodine, which is a nonmetal. We see oxygen, which is a nonmetal. So that tells us it's type 3. Really just need to count what's there and use the appropriate prefix. So prefix for 2 is di, and that is iodine, full name. Prefix for 7 is hepta, and we'll drop the A there and become heptoxide. Again, the 2 I's are okay. Mainly the A and the O, and the O and the O is not so good. Any question on that one there? This is carbon nonmetal. This is oxygen nonmetal. So again, it tells us it's type 3. We only have one carbon. Prefix for 1 is mono, but again, we do not use it on the first name. So we just use the element name, which is carbon. Prefix for 2 is dioxide here. So that would be carbon dioxide. Last one here on the left, we have P, which is phosphorus, and Cl, which is chlorine, both again non-metals. Once again, mono for the first guy we do not use, so we'll just use phosphorus. And prefix for 3 is trichloride. Any question on any of those names there? Going to the right, I think probably the easiest of all naming stuff is writing the formulas for these guys. There are prefixes. That's all you have to worry about. So dinitrogen, di is 2, nitrogen is N, so that's N2. Tri is 3, sulfide is S, so N2S3 would be our formula. Carbon, no prefix, but we do see a prefix here, and they're both non-metals, so that tells us no prefix on the first one. There's just one. And tetra is 4, and chlorine is Cl, so CCl4. And dioxygen and pentanitride, di is 2, so that's O2. Penta is 5, nitrogen is N, O2 and 5. Any questions on type 3 compounds? Again, I would say the easiest, but a lot of times people screw them up for some reason. Yes, they try to do weird things. Any questions on type 3 naming? All right, last little bit we're going to talk about is something we talked about a little bit earlier, which are hydrates. Just to remind you how to name those. A hydrate is basically two parts, as we talked about. It's a salt and a water part, right? And they're usually connected by this little dot in their formulas. So if we have something like MgSO4.7H2O, we basically named the salt part like either a type 1 or 2 sort of compound, and the water part gets the word hydrate with the appropriate prefix. So once again, this would be type 1 metal. So that would be magnesium, sulfate, 7 is hepta, and then hydrate for the water here. So kind of a combination of a couple of those things, kind of a combination of prefix and a combination of type 1 and type 2 together. If we had copper, Roman numeral 2 nitrate, trihydrate. So if we were to write the formula, we'd do the same thing. We would just tackle the first part here. There's copper, Roman numeral 2. That means the copper has a +2. Nitrate is NO3 minus. So in this case, we need more of the nitrate when we put it together. We need a total of 2, so we do need to put parentheses around it. We would put the dot between the salt part here and the water part, and trihydrate means 3 water. So that would be the formula. So hydrate's not too bad. Basically a type 1 or type 2 for the salt part, and prefix and hydrate for the water part. Any questions on hydrates? Any questions on any of the naming that we talked about here? All right, so obviously you are responsible for the naming part. All right, then we are off to going to talk about atomic mass. We're also going to talk about grams, moles, Avogadro's number, and we're then going to talk about officially how to calculate empirical formulas and molecular formulas and all that good stuff. So let's start with atomic masses. So one of the fundamental properties of an atom is obviously its mass, which is related to the number of protons, electrons, and neutrons that we see. It is actually the number that we see on the bottom of the periodic table there underneath the symbol, is its atomic mass. We can't really obviously pick up an atom and put it on a scale as it's really small. So typically in science, especially in chemistry, when we can't sort of directly measure something, one way that they do it is they pick something to use as sort of a standard to compare everybody to. Either they give it a mass or they give it a value. And for atomic mass, they actually picked an isotope of carbon to use as the standard to compare everybody to. And it was the carbon-12 isotope. It had 6 protons and 6 neutrons, and it had a mass of exactly 12 AMU, which is atomic mass units, sometimes called a Dalton. We really won't use AMU all that much in most cases, but that technically is the number that we get from the periodic table, is how many AMU there is in an atom, is basically what we see there. So an atomic mass unit is equal to 1/12 the mass of the carbon-12 atom. So the atomic mass or atomic weight was found for most of the elements up there on the periodic table by doing experiments and finding, for example, something like hydrogen is about 8.4% as big as the carbon-12 isotope. So they do a little math here. That's basically 8.4% times 12, which is the atomic mass there of the carbon-12 isotope, gives us something like 1.008 AMU, which is the atomic mass that we use for hydrogen. Similar calculations can be found obviously on the periodic table. And again, sort of unit-wise, when you pull off something from the periodic table like that, that basically is 1.008 AMU in an atom, is one sort of version of units that we could use with that number. For most cases, when you do pull that number off the periodic table, which we'll use it more so for molar mass, which is grams per mole, typically we take it to about 4 significant figures. So it's usually kind of what you take off the periodic table is about 4 significant figures. Now, if they use the carbon-12 isotope as the standard, and it had a mass of exactly 12, when we look at carbon, we do not actually see 12, but we do see 12.01 as the atomic mass for carbon. And really the reason for that is what we see on the periodic table is actually the average atomic masses. They are the average atomic masses for all the naturally occurring isotopes for a particular element. So for example, carbon-12, carbon-13 for carbon, there are the naturally occurring isotopes for that particular element. So although we don't usually describe it as average atomic masses, and we just call it the atomic mass, they are actually those average values for all the naturally occurring isotopes that are there. So how we find the atomic mass of an isotope or an element is we do a little formula that the atomic mass is equal to the percent of the first isotope times the atomic mass of the first isotope. We then add it, not multiply or anything like that, but actually add it to the percent of the second isotope, bless you, times the atomic mass of the second isotope. And if there happens to be a third one, you just kind of continue that pattern. The percentage is basically sometimes referred to as percent abundance, percent relative abundance is basically the percentage at which that isotope naturally occurs sort of in nature. Obviously, if you have all the naturally occurring isotopes, the percentage should add up to 100%. Yeah, so if it doesn't, then you're missing something. But that's basically what the percentage is. It's sometimes referred to as percent abundance, percent relative abundance. Again, it is the percentage at which that isotope basically occurs in nature. So if we look at something like carbon, we see that the carbon-13 isotope and the carbon-12 isotope are the two isotopes that occur, and their natural abundance is carbon-12 is about 99% of the time, and carbon-13 is about 1% of the time. And we can use our formula that we just did there and take it. This is basically the 98.89%, right? Move the decimal place 2 places to the left, or divide by 100, whichever way you want to do that. That is the atomic mass of the first isotope. That is basically 1.11% converted into a decimal times the atomic mass of the second isotope. And when you do that, you end up with 12.01, which is the average atomic mass that we do see on the periodic table. It's important to note that these are just average values, and they are values that we use in calculations all the time. But you'll never ever really find a carbon guy that has a mass of 12.01. You find like a carbon-12 that has the mass of carbon-12, or you find a carbon-13 that has a mass of carbon-13. There really is kind of no one that is 12.01. Any questions on that there? So atoms have very small masses, and an atomic mass unit for relationship to grams is 1.66 times 10 to the minus 24 grams. As you can see, a very, very small number. Now, if we wanted to do some just straight up conversions about the mass in AMU of 431 atoms of carbon, we would go and get this from the periodic table. And again, we oftentimes don't use these units too much anymore. We use grams per mole mostly, but we can see it's 5176 AMU here, and we could do it as a conversion factor. Same thing here with aluminum. We look under aluminum on the periodic table. We'll say 2698, which once again is where that comes from. Once again, using it as a conversion factor, our atoms here will cancel, giving us the AMU of 75 atoms of aluminum. Now, how do we figure out sort of the masses there of these isotopes? Are relative abundance. One way is to use something known as mass spec. Mass spec basically has atoms that are ionized. They're sent down a tube. They go through sort of an electrical magnetic sort of field, and they're basically separated out by fragments of size. Some molecules are broken down in the ionization process. It gets bent, and again, it really sort of separates out on the graph based on their masses. And this is sort of a mass spec sort of graph. And again, you can figure out the percentage that each of these isotopes, and chlorine 35 versus 37 will come off at different sort of peaks when it goes through the mass spec. There's sort of a picture of it. Once again, our sample comes through, gets heated up, comes through an electrical field, gets sort of bent by the magnetic field, and again gets separated out by mass. Kind of lightest particles there to the left in this picture, heavier particles over there to the right. So why don't you take a second here, and why don't you calculate the atomic mass of based on these two. Okay, let's take a look here. So we're looking for the atomic mass, so we will use that sort of formula that we just talked about there. Again, it's the percentage times the AMU of the first isotope, first the percentage times the AMU of the next isotope, and so forth. In this case, we have two copper isotopes, copper 63. That is 69.17%. and has a mass of 62.9396 AMU. We also have copper 65 here. Doesn't give us the percentage, but does tell us that it is 64.9278 AMU. We do need the percentage there of copper 65. We could get it by assuming what? We'd assume that we have 100% would be everybody, right? So if it's already 69.17% of our copper 63, that means the percentage for our missing guy there should be about 3083 here. So you could assume obviously that these would be 100% of all the naturally occurring isotopes, and now again, find the missing percentage. At this point, you got everything you need. You could go the atomic mass here, going to be our first isotope. We do need to convert our percentage into a decimal. So you're divided by 100, just move the decimal place. A couple places to the left there, times it by the 62.9396 AMU, plus our other percentage, also moving the decimal over to convert it into a decimal point there instead of a percentage. 64.9278 AMU. And if we do all that good stuff there, it's like 63.55 AMU, which is pretty much what you see on the periodic table there underneath copper. Yes. Any questions on that calculation there? That is. All right, so next thing we're going to talk about then is everybody's favorite thing, which is moles. So a mole, and the abbreviation for a mole is MOL. They had to abbreviate it some way, so they got rid of the E. So when you do see MOL, it is the abbreviation for mole. It's not the abbreviation for molecules, which is sometimes mistaken for. And it's the amount of substances that there contains in as many atoms of 12 grams of the carbon-12 isotope. 1 mole of anything will equal Avogadro's number, which is 6.022 times 10 to the 23. Now, the units on Avogadro's number vary depending on your use of it. Atoms, they could be molecules, they could be pizzas, they could be shoes, and so forth. Most of the time in chemistry, probably these two. Occasionally the pizza pops in, but usually it's atoms and molecules is usually what we use it for, sometimes particles as well. It is our conversion factor to basically go between those two units. It's our conversion factor to go between, obviously, moles and atoms or molecules and backwards. So sometimes people want to use Avogadro's number everywhere in a calculation, and you shouldn't do that. You should only use Avogadro's number if there's some mention of atoms, some mention of molecules, or you're asked to find something in atoms or molecules. If they really don't mention that, you should leave Avogadro's number on the side. So that is basically what a mole represents. Again, the idea here is kind of like when we say a pair of something, it represents 2, or if we have a dozen, it represents 12. So when we say a mole, we have that many atoms. You could do it for anybody on the periodic table. 1 mole of hydrogen would be 6.022 times 10 to the 23 atoms of hydrogen. You write 2 conversion factors for that. 1 mole of hydrogen over 6.022 times 10 to the 23 atoms, or vice versa, 6.022 times 10 to the 23 atoms over 1 mole of hydrogen. So you could use it as a conversion factor. You could also use it, obviously, for something that is not just an atom. Like if you had 1 mole of water, you would have 6.022 times 10 to the 23 molecules. Here we would use molecules for the unit, as water is a molecule rather than just an atom by itself. So again, works the same way. You can write 2 conversion factors for those as well. Now, another really important sort of conversion factor that we use a lot in chemistry is molar mass. And molar mass is how many grams there are per mole. And that is typically what we use the number on the periodic table for underneath. That number right there basically tells us there are 12.01 grams in 1 mole of carbon. Our carbon's molar mass is 12.01 grams per mole. We could use molar mass as a conversion factor as well. So you could do dimensional analysis and go 12.01 grams over a mole for carbon, or a mole of carbon is 12.01 grams. So you could do it either way and really use it as a conversion factor. We could also use it as a conversion factor for things that are not just atoms by themselves or anything like that. We could do it for water as well. For water, we would just add up all the parts. So there are 2 hydrogens at 1.008 grams per mole, plus an oxygen at 16 grams per mole, gives us 18.02 grams per mole as the molar mass for water, which once again you could use as a conversion factor of 18.02 grams per mole for water. Or you can flip it around and do 1 mole of water, 18.02 grams. So molar mass is really nothing more than really a conversion factor, and it is the main conversion factor we use a lot in chemistry to go from grams to moles, or moles back to grams. Now, for any element, the atomic mass in AMU is the same as the molar mass in terms of numbers. So they're exact same numbers. It will convert out the same because you use Avogadro's number and the gram number, and it all works out the same. So most of the time when we do pull that number off the periodic table, like I said, it will be used in the molar mass sense, grams per mole. Same rule here. We still use 4 significant figures when we pull it off. The relationship between all those, how they all tie together, is if you have 1 mole of hydrogen, that would be 6.022 times 10 to the 23 atoms of hydrogen, which would have a mass of 1.008 grams. So that is how they all relate to each other. They're all equal to each other, basically. They're all basically saying the same thing. Any questions on molar mass there? All right. This is a mole of all these different elements, and they may not look like the same amount, and that's because a mole, for example, something like sulfur is 3207 grams, right? And a mole of something like hydrogen is 1, or carbon is 12. So a mole does represent a different mass for each of those different elements. Once again, here's the relationship between AMU and grams. And basically, since it's Avogadro's number, everything comes out the same. All right, let's try a couple here. Let's calculate the number of grams in 15.7 moles of iron. You go to periodic table and look at iron, it will say 5585. See what you come up with. Okay, let's take a look. So we're looking for grams and we have moles. So we do not need Avogadro's number here. So there's no mention of atoms, molecules, or anything like that. Remember, pretty much our conversion factor from grams to moles and backwards is the molar mass that we get from the periodic table. So we will take 15.7 moles of iron. We will use our molar mass here that we can pull off the periodic table, and that means 5585 grams per mole. Or again, you can use it in sort of the opposite fashion if you're doing a little dimensional analysis. Good chemistry setup here. So we'll use a little dimensional analysis sort of approach here, and we will set up the moles so they cancel, so they go on the bottom. The 55.85 grams go up on top. We're basically multiplying 15.7 times 55.85 gets you a lot of numbers there. 876.845 grams, which obviously I should take down to 3 sig figs off of that number there. Gets us about 877 grams of iron. Any questions on that one there? All right, let's try a couple more here then. Okay, so once again here, we got moles, we got grams. So again, we're just really doing a grams to moles type of conversion. So once again, that's going to be our molar mass from the periodic table. That again means 6.941 grams per mole, or a mole is 6.941 grams. Starting with the 77.8 grams of lithium here, we want the grams to cancel, and that's going to give us 6.941 grams on the bottom, a mole lithium up on top. We are dividing here, 77.8 divided by 6.941, going to yield us about 11.2 moles of lithium in this case. Yeah. Any questions on that there? All right. All right, let's try this one. How many atoms are there for 0.55? Okay, let's take a look at this one. So this one, we do see atoms, which is a key that perhaps we should use Avogadro's number. And to use Avogadro's number, that's basically moles to atoms, which means I need to get to moles, and we're starting in grams. So we do need to go molar mass first to get to moles, and then Avogadro's number there to go from moles to atoms in this case. So once again, starting with the molar mass in the periodic table, that would be 39.10 grams per mole. Or a mole is 39.10 grams. So starting with our 0.551 grams of potassium, we're going to divide out the grams there. So 39.10 grams per mole of potassium. We stop right there. We have got rid of our grams. We're in units of moles. So we'll use Avogadro's number, which is 6.022 times 10 to the 23 atoms equals 1 mole. So since moles are on top, we want moles on the bottom here. So a mole of potassium would be 6.022 times 10 to the 23 atoms. The moles cancel. So we're multiplying across the top there, which would be 0.551 times Avogadro's number. Make sure to use your exponent button, hit equals divided by 3910, going to get us 8.49 times 10 to something 21, I think it says. 21 atoms of potassium here. Any question on any of those steps there? You obviously could get a number after the first sort of division there and then multiply it. Just try not to round it probably till the end as well would be good rule of thumb there. Any questions on this one? All right. So a few more here. Try helium and zinc. So let's do helium 4.003. Zinc, it depends on your periodic table these days, 6539. All right, so let's take a look. We're looking for moles on the first one. We have grams. So once again, this is just molar mass. So this should become very routine as we do it a lot. So we got 5.46 grams of helium. Once again, go into the periodic table to use that as a conversion factor. We want to get rid of the grams, so the grams are going to go on the bottom, so they cancel. Moles of helium, once again here, the grams will cancel. We're dividing 5.46 divided by 4.003, going to give us a 1.36 moles of helium in this case. Any question on that one there? Second one here, we're looking for grams and we have moles. So once again, that is a molar mass situation. So we're going to start with actually moles in this case. And we're going to use our periodic table here and our molar mass. And we're going to put the grams up on top in this case so that we cancel out the moles. Moles cancel. And in this case, 0.256 times 65.39. 16.7 grams of zinc in this case. Any question on either of those two? All right, let's take a look. I'll skip this one here. But let's do let's take a look at this one here. We want to know how many hydrogen atoms are there and 72.5 grams of C3H8O. Now, sometimes we're not interested necessarily in the entire sort of compound here. We're definitely just interested in the hydrogen part. We are looking for atoms of hydrogen, which means Avogadro's number is probably going to go there. In order to get there, once again, we do need to get it into moles to get to Avogadro's number. And obviously, we're starting with grams here. But along the way, we do need to go from this entire thing to just the hydrogen part. So we can't kind of do it like normal. We can start with converting it into moles. And before we do that, we could look at the actual formula. And when we see a formula that is C3H8O, all of the numbers on the bottom here represent the moles of each of those guys. So we could actually come up with some relationships from the actual formula that will help us do that. So for example, we could say in 1 mole of the entire thing here, there is 3 moles of carbon. And that 3 obviously comes from the formula. In 1 mole of the entire thing here, there would be 8 moles of oxygen, which also again comes from the formula. And we could say in 1 mole of the entire thing here, there is 1 mole of oxygen. Actually, that would be 8 moles of hydrogen would be a better one on that second one. That should be hydrogen. There you go. So we could actually come up with 3 sort of conversion factors that we could get from the actual formula. And it's a mole to mole sort of relationship. So that does mean we do need to convert these grams into moles. So we do want to start by converting the whole thing into moles. So we do need the molar mass of the whole thing. So our molar mass of our C3H8O, basically just adding up the parts. That's going to give us 3 times 12.01 for our carbon, plus 8 times 1.008 for our hydrogen, plus a 16 from our oxygen. And all those numbers obviously come from the periodic table. And if we add up all those numbers there, 3 times 12.01 plus 8 times 1.008, which is our hydrogen molar mass, plus the 16, which is our oxygen molar mass, we end up with a molar mass of 60.09 grams per mole as the molar mass here of this particular compound. Any questions on that there? So we're going to use that to start our conversion here. We're going to go 72.5 grams of the entire thing. And since we need it into moles, we're going to use the molar mass we just calculated, which was 60.09 grams per mole of the entire thing here. Now, as we could see from the problem, we're interested in just the hydrogen. So now that we have it in moles, as these grams cancel, we can now use our relationship from the equation, our formula, to go from the entire thing to just the hydrogen part. So that's what we will do next. We will go from 1 mole of the entire thing. There is 8 moles of hydrogen. Any questions on that there? Once again, the moles of the entire thing cancel, and now we're left with moles of just the hydrogen, which is actually pretty close to what we want. We don't want moles of hydrogen, but we want atoms of hydrogen. So that is where our friend Avogadro and his number will come into play. So we will now just use Avogadro's number to go from moles of hydrogen to atoms of hydrogen. Once again, here we want the moles to cancel. So we're going to put the moles on the bottom. And we're going to do Avogadro's number up on top. And these would be atoms of hydrogen. The moles cancel. Now, doing all that there, we end up with 72, whoops, not that, still not that, 72.5 times 8 times 6.022 to the 23, it equals, divided by 60.09, looks like we end up with here 5.81 times 10 to the 24 atoms of hydrogen. So again, sometimes you may not be interested in the entire sort of formula there. You may just want one element of it. You could use the actual chemical formula as a mole to mole sort of relationship and conversion factor to allow you to get there. Obviously, if I didn't want atoms of hydrogen, but I wanted grams of hydrogen, I could use the molar mass at the end, right? I figured out how many grams of hydrogen that would have been. So you could also do it that way if you want something like that. Any questions on that there? All right, so why don't we try these two here? I'll give you some numbers here. Carbon is 12.01, hydrogen 1.008, oxygen is 16. While we're at it, how many grams of carbon would there be? Starting with the same amount, obviously. Okay, let's take a look and see. We'll start with the first one, which is we're looking for how many moles there are in this many grams of ethanol. So obviously grams to moles, molar mass is what we need to start with, perhaps. So we're going to get the molar mass of C2H6O. So that would be 2 times the molar mass of carbon from the periodic table, plus 6 times the molar mass of hydrogen from the periodic table, plus 16, which is the molar mass of oxygen from the periodic table. That's going to get us 2 times 12.01. Thank you, 46. That was good. So 4607, we'll call it. How's that? 4607 grams per mole. And we will use that for our molar mass here. We'll start with 23.2 grams of C2H6O. We're going to divide by 4607 grams per mole. And we will get there 23.2 divided by 4607. Call it 0.504 moles of C2H6O. We basically can continue on in the next part of the problem because now we're going to molecules, which is sort of the key word there that we need Avogadro's number to do that. We already have it in moles here, so 0.504 moles of C2H6O. Using Avogadro's number here, we're going to do a mole on the bottom and Avogadro's number up on top so that we do end up with molecules. The moles will cancel and we get, bless you, 3.03 times 10 to 23 molecules of C2H6O in this case. First off, any questions on either of those two? Yep. Yeah, so if you have grams and you want moles, you're always going to be dividing by the molar mass. And obviously if you have moles and you want molecules or atoms, you'll be multiplying by Avogadro's number. Yeah. Other questions? Now look at the bottom one there. We want to know in this case how many grams of just carbon would there be in this amount of ethanol. So this is once again where we could use the actual formula as a conversion factor. And from the actual formula here, using our bottom numbers as moles, we see in 1 mole of the entire thing here, we have 2 moles of carbon. So that's going to be really our way to go from, again, the whole thing to just carbon. Obviously, to do that, we would need the moles of the entire thing, which we actually calculated right here. So we can actually just pick up with that number. Obviously, if you didn't do that, you would need to do that first to calculate the moles of the entire thing. But since we did, we'll just pick it up with that number there. And using our conversion factor from the actual formula, once again, we want to get rid of the entire thing. So that will go on the bottom. And the 2 moles of carbon will go up on top. At this point, we're now into moles of carbon, which is close to what we want, but we do want grams. So once again, we're going from moles to grams. So we will use the molar mass for carbon to do that from the periodic table. And it would be 12.01 grams per mole of carbon. The moles of carbon will cancel. And at this point, we will end up with 0.504 times 2 times 12.01, about 12.1 grams of carbon, if I got that right there. Any questions on that there? So you oftentimes, obviously in chemistry, use grams of moles a lot in calculations that we do. So obviously using the molar mass is a lot. I'll be honest with you, probably not a lot of Avogadro's numbers used in a lot of calculations, but definitely molar mass is, but you do need to obviously know how to do that. So any questions on how to calculate grams, moles, atoms, individual elements?